Okay, so today what we will do is update our equations and see how to add this additional rotating magnetic field, and in the process make this magnetization vector fall to ground. Notice that we were talking about alpha, right? Alpha had to be 90 degrees to make it to the floor, so you get the maximum signal, right? In the signal equation, if you see, there is a sign alpha, so the magnitude becomes maximum when the alpha is 90 degree. That means you have to add additional magnetic field, which is rotating magnetic field, that will help us push this magnetization vector onto the transverse plane. How do we do that? How do we upgrade our equation will be the topic of interest today. Okay. So how do we tilt the M vector to a initial angle? So clearly, as we've been talking about, read the text in this section. They have given step by step how to understand this, but clearly we did this thought experiment yesterday, right? So if you already having the magnetization vector precessing around, right? So you have it like this along the z direction, around the z axis. If I just apply one, right, to push it to floor, this cannot happen. So we talked about how to do this. You have to be going along with the precision. So you have to apply this field that should also go around, right? That should also be having the same frequency. Only then you can constantly push it down. So that is the intuitive process. So therefore we apply a circularly polarized magnetic field. So what do they mean by circularly polarized? If you were to track the path of your additional magnetic field, right, your B1 field, then it will look like a circle in the XY plane. That is what they mean by circularly polarizing magnetic field. It has to be applied at the same Larmor frequency. If you do that, you could essentially tilt the back. So I am doing this because in the XYZ coordinate, this is what is happening. But if you want to visualize this easily in the rotating frame of reference, essentially what happens is this magnetization vector is going to the floor. Okay. So you apply B1, right? B1 of T is nothing but it's having a envelope, and then it is having a frequency here. So that is the description of the rotating magnetic field. So it has two components, X and Y. That's why it is able to move in the XY plane. So you apply this using a quadrature RF coil. We'll talk about this coil design and other things in the instrumentation aspect when we go forward the next module. So simplest way to think about this envelope is a rectangular envelope of the pulse. So you have this rotating magnetic field that is switched on and switched off. So you have, when it is on, it is having the same amplitude. That's what this envelope is saying, right? Okay. So how is the motion? Motion, we have seen few animations, so I know it should be intuitive. The motion is going to be spiral, right? So here is an example to understand. So left in A, what you see is the representation in the rotating frame of reference. So you see the axes are X dash, Y dash, Z dash. So as a thought experiment, right, just to make yourself comfortable, if you actually imagine, what did we say? Initially, when we applied a static magnetic field in the Z direction, the precession was around Z direction. That is, your magnetic vector started to precess around Z direction. Now, if you look at Z dashed, right? So you have M. If I apply my B1 in X dashed, what should happen? So I have a vector in Z dashed. I am applying another magnetic field in X dash. So where should be the motion of the M? It has to rotate around B1 or rotate around X1 axis. That means it has to move from Z dashed to Y dashed, right? That is what, when we applied in the Z direction, it started to rotate, precess around Z direction. If now B1 is applied in X1 direction, the magnetic moment has to precess around X1. And intuitively, that's what it is, right? So However, in 3D coordinate, if you see, it is going to be, which is shown in the B, it is going to be a spiral. So it is all consistent. You have to train yourself to visualize this further. Okay. So now, how much do you want to tip it? So idea is I want to tip it. I know how to tip it, which is apply additional B1 field, which is a rotating magnetic field. If I apply that, I will be able to do it. So how much should I tip? That is your tip angle. So I will get tip angle depending on your alpha is equal to gamma times 0 to tau p. So how much ever time I have this RF pulse, right? Excitation pulse, what is called as excitation pulse on is going to determine the, so if I have it long enough, it is going to try to push it down as much as possible. If I just have it on and off, then I may just move some angle, but I might not have gone fully. So the amount of time that you switch on this excitation is going to determine the angle to which it is going to be pushed. So the alpha is the angle, tip angle, right? So for simple case, if you assume it to be a rectangle, then your alpha is nothing but gamma B1 tau p. Tau p is the time duration over which this pulse, excitation pulse is on. The simplest case of rectangle, I just get 0 to tau p minus 0, right? So gamma B1 tau p. So now we introduce some jargons. So we talked about this. Your magnetization vector, when it falls on the floor, right? Your sine alpha, remember the signal magnitude had a sine alpha. So you get maximum signal when alpha is 90 degree or pi by 2. Therefore, any pulse that you apply that is used to push the magnetization vector by pi by 2 or make the alpha equal to pi by 2 is called as a pi by 2 pulse, right? Very intuitively named. Pi by 2 or pi over 2 pulse. What this does is when you apply a pi over 2 pulse, that means it implies the excitation magnetization vector has been excited and pushed to the transverse plane, which will elicit maximum signal, right? You remember MXY, the transverse component gives you the signal, right? That gets you the maximum signal if it is on the floor. So naturally there can be other variations. If I apply long enough, right, I could also make alpha become pi. What does that pi mean? So I was here, 90 degrees is here, 180 degrees is going down. So that means it's an inversion pulse. So why would you want it to align in z direction, right? Already z direction, we talked about signal being coming in the xy plane. If I push it to pi, which is an inversion pulse, it doesn't give me much, right? I need signal to be on the floor plane, not perpendicular to it. However, this is a very important signal, pi by 2 pulse excitation, because we'll talk about this in the next lecture module, because this will be used to do spin echo, right? So this is important as well. But again, you won't apply inversion directly. If you apply 180 degrees, you don't get much because there is no transverse. So think about what happens if I apply pi and then pi by 2, right? Let's leave it there for now. So essentially, you also call this excitation pulse as a alpha pulse, because remember you are trying to manipulate this alpha. Okay, so you could understand from this, more or less the terminologies and the variables used are also very consistent and standardized. So you cannot just say, oh, I am used to saying angle to be theta or phi or something. And here it is very standardized. So alpha pulse means alpha is this angle of magnetization vector with respect to your z axis or the primary static field axis. So pi by 2 is essentially the signal, maximum signal that you get in transverse. So it is also called as alpha pulse. So now we need to talk about exciting. Exciting something is fine, but then excitation cannot survive for long. The moment the excitation pulse is done its job, that is pushed, you have had the excitation pulse on for tau p. So you made sure that you pushed it. So I'm just deliberately stopping somewhere. If it is 90 degree pulse, it would have been like this. So I can stop anywhere I want. So I've essentially excited it, right? It is now what some signal is there. Now the excitation pulse is off. What is going to happen? I mean, ideally speaking, you have created the coherence, it will keep doing this. But nature is not like that. There has to be some loss. Nothing is perpetual in life, right? So what happens is, the moment you take the excitation, they all try to obey the command only till the excitation is there. But thereon, the nature kicks on. The moment the excitation pulse is off, they all start to lose their coherence. Therefore, what will happen if they lose their coherence? Signal strength will start to go. Or the process is called as relaxation. Initially, you're adding B1, you're forcing them to, come together and pushing them to flow. Here, in some sense, you're forced. So that is forced precision. Now, you're allowing it. You have removed the excitation. You have removed the force. Then it has to relax. It will relax, and what will happen? It will relax, everything will dephase in the XY plane. If you see, all the phase will be in different, all the vectors will be in different directions, and eventually they will try to align themselves to having only Z component in the static field, right? That is what relaxation process will happen. So naturally, that means we need to talk about it is losing signal strength. So in the relaxation process, how all can it lose signal strength? One is dephasing. The moment it starts to dephase, you have lack of coherence, signal coherence, and therefore lack of signal. The relaxing signal is dying down. That is your transverse component. There is other process also, right? Once the signal coherence is done, the signal is going down in the transverse. Your Z axis, it is getting built up. Your longitudinal component is building up, right? That is relaxing to gain signal strength, whereas the XY components relax to lose signal strength, right? So there are two aspects to it, and we will kind of break the two aspects and talk about what it is called. Okay. So there are broadly two ways of relaxation. One is the dephasing part, which we call as transverse relaxation. Very intuitive, right? This is a transverse signal that we got because the XY, we made everything coherent. So we made everything come in phase. So the moment the excitation pulse is off, or the rotating B1 pulse is off, it is going to start to dephase. How it is going to dephase? We'll talk about the physics and some aspects of it. Then the other one is energy loss. Meaning, when you start to lose energy here, again your Z component is going to increase. So that is your longitudinal relaxation. So it is coming to all the excitation that you put in, the extra energy that you put in is lost. So it will come back to its resting state in static magnetic field. So there are two aspects of relaxation. The first one you could think about this way. How did you get a signal? Because of phase coherence. What do you mean by phase coherence? I applied, each one is a different phase. What did we talk about different phase? That means all of them are now aligned, and of course they all have the same frequency, or supposed to have the same Larmor frequency. So they are all in alignment, even though they started differently. The excitation pulse made sure they all align, they all come together and then precede with the same frequency. So now what happens is, if you take a molecule, that is fine. Now we are talking about the bulk, right? In the bulk, each nuclei is not just a nuclei by itself. It has it's part of an atom. The atom is part of a molecule. So it has surrounding neighbors. Neighbors can be whoever. So essentially, one spin can interact with another spin. Okay. So one spin interacts with other spin means what happens? Some spins can be slightly faster. Some can spin slightly slower. Even though we said all of them have the same omega, like the precession frequency, there could be slight differences because it's all surrounded by, each nuclei is surrounded by different nuclei, number of nuclei that is there, number of other nuclei that are there. All this is slightly different. So what happens with slight difference? That means some is processing some more, the neighbor will be processing some less, and therefore they are not exactly the same value. So the moment the external excitation is off, the small differences starts to make them fall apart. They were all one. Now they are falling apart because there is a small differences, and with the time, each one will, the difference will become bigger and bigger. So that is the natural laws. This is also called as spin-spin interaction, right? So because there is one spin, there is another spin, they all interact with each other, and therefore there is a change in the local magnetic field. You can look at it whichever way. Magnetic field changes, your omega changes. Small this thing changes omega, therefore your magnetic strength also changes, right? So this makes the signal to decay. And then there is a relaxation time T2 and T2 star. Okay, so that means it starts to relax due to dephasing. That there are two phenomena. We'll label it as T2 and T2 star. Right. The other one is spin loses its environment, energy to its environment, and then it the Z component comes back up. This relaxation time we will call it as T1 time. That is, after you switch off the excitation, how long does it take for the mz to build up and come back to the equilibrium value? The time constant we will call as T1. So we'll have to strictly define these T1 and T2, T2 star. So let's start with the T2, the dephasing part, right? Transverse relaxation. So the strength of the magnetic field in the immediate environment is different. That's what I told you, because it is not homogeneous. There's small differences in the surrounding of each of the nuclei, and therefore the spin-spin interactions make sure that the each of the nuclei, some spin slightly fast, some spin slightly slow, and therefore there is a dephasing. So with the time, what happens is all of them become out of phase. When they become out of phase, signal coherence is lost, so signal goes down. So this reduction in signal due to spin-spin interaction, we call it as T2, transverse relaxation. Of course, the rate at which it goes down, right, as a time constant, which we'll shortly name. So here is the process that we are talking about. Initially we had, notice it is all Z dash, X dash, Y dash, meaning I am not going to do this. I am sitting in the circular rotating frame of reference. So I have the magnetization vector. I put a pi by 2 excitation, so it has fell down. After I stop the excitation pulse, after it moved down, what happens? Immediately it will start to dephase, right? Dephase, and therefore the signal starts to go down. The coherence, the signal starts to go down, because remember, this is the magnetization that is giving you the signal, transverse mxy of t. With you allow in some more time, full dephasing happens, and then what happens? The mxy component eventually goes to 0. So your transverse relaxation decay. So if we add this mxy from before, now what we have added is, this is a practical process. You don't just keep doing mxy forever. There is going to be a decay, and the decay in this case is modeled as an exponential decay with time constant T2. That is, T2 describes how fast it dephases, or how fast the signal is getting lost in the exponential model. So T2 is called as the transverse relaxation time, which is the time mxy to decrease by 1 by e. So this is also called as spin-spin interact relaxation time. Just to be clear, that T2 has to do with neighbor spin-spin interaction, and therefore changes. So now the question is, okay, that is all fine. There is a small change due to spin-spin interaction, and so it dephases. Then what does T2 star mean, right? Okay, we'll come to T2 star after it. Okay, this is, you got your signal. This is your mxyt, but this is not. I mean, this is just the interpretation of how do you capture this signal. That part we have not finished, but we talked about this. How do we do it? Magnetic field, right? Mxy vector is rotating in the rapidly rotating in the transverse plane. If I put a coil, what happens? Magnetic flux cuts this coil, current comes in, and then you get the free induction decay voltage, right? So the signal that you actually measure is a voltage signal that we talked about yesterday. So what happens here is dephasing. Initially you have the magnetization vector, and then it starts to relax. When it relax, dephases means the transverse component is going down. Transverse signal is decaying. Energy loss causes the longitudinal component of magnetization to recover to the equilibrium value. Of course, you'll have to notice these are happening simultaneously. Dephasing is happening at the same time it is trying to go up due to other losses, right? So simultaneously this is happening, and therefore what you actually measure is going to be something like this. First, when you are applying excitation, right, then it is dephasing. Only when it is on the XY plane, right, this will play again. Okay, look at the different variations. You can play this several times to understand, but notice the process that we are interested. Initially, when you excite, there is no signal. The M has to come fall on the floor. The moment it falls on the floor, you get the maximum peak signal, right? And then the M starts to reduce because of dephasing. So the signal goes down. How fast it goes down is the material property of T2 T2, right? And then while it is going down, the M in the Z direction is increasing. Okay, that's so your T2. So your signal is recorded, voltage signal is recorded, but it is getting reduced with the time. And the rate of reduction is going to define your relaxation time, dephasing relaxation time. Okay. While you also notice that due to energy loss, the signal in the Z direction is increased. So the voltage signal is produced by MXY, also decays. This is called as the free induction decay. This is the signal that you are measuring. Okay. Now the question is, okay, we saw something as T2 star. What does that T2 star mean? Notice how all the signal can lose its magnitude. Dephasing, right? When it is dephasing, that means there is a difference in frequency, subtle difference between the frequencies of the neighboring nuclei. One, we talked about spin, that the neighboring elements, right? Neighboring nuclei can affect the spin interaction, causing some to spin fast, some to spin slower, slightly around the plus or minus the omega frequency that you have, the Larmor frequency. But notice you also have a magnetic field B naught. What happens if the magnetic field is not homogeneous? Meaning there are fluctuations, right? It cannot be perfect. So you have a base B naught, but there are small imperfections, and therefore you have B naught plus delta B naught, or small changes, or plus or minus. Then what will happen? If a region is experiencing more B naught, more than B naught, it is going to precess faster. Remember the relationship between omega and B naught. So if I increase my B naught, omega is going to increase. So if there is going to be a small imperfection which makes the B at that location greater than B naught, then this is due to static field, right? Then that is going to have slightly more Larmor frequency. The other one, if it is slightly less, it is going to have less. So there is inherent imperfections in the magnetic field, which is systemic, right? This is not about the material. Spin had to do with the material property, whereas this one is the systemic, is the magnets that you have, the permanent magnet, that the static field that you are creating. If there are imperfections there, then that may cause, and nothing is perfect. So the small imperfections cause small difference in the omega. So in the absence of any excitation which is strong enough, these imperfections make the nuclei magnetization vectors which were in phase to start to rapidly dephase. So this accelerates the process. So that is called as your T2 star. Both are relaxation due to dephasing, but one is due to magnetic imperfections in the static magnetic field, which is T2 star. The other is your T2, which is to do with your spin-spin interaction. Okay. So T2 star is actually causing faster decay. So you have dephasing due to two relaxation process. One is spin, the other is due to the variations in the static magnetic field. Okay, so why is this important to study? This is important to study because the initial rapid drop happens due to T2 star, and you don't have control over. It's the magnet that you are using, the magnetic field that you are generating. You don't have control. Whereas T2, you see, retains the signal for much more duration. So perhaps if you want to play this game multiple times, it will be prudent that T2 is much greater than T2 star, and therefore you may have some cushion in pushing, getting the signal, allowing it to decay, measuring it again. Easiest way is I allow everything come to equilibrium, push it to floor, measure T2. Right? Initially it will be T2 star. I can done with, but you may want to do multiple measurements, right? And therefore it will become prudent that you can exploit T2 because the signal is there for a lot more time than T2 star, which is a systemic accelerator. Okay, so let's talk about this little further when we talk about how do you apply multiple times. If you apply the pulse, this will become little clearer. So last part on the relaxation is your raising exponential. What do I mean by raising? The longitudinal relaxation, the MZ. The dephasing happens, signal reduces, complete dephasing happens, your XY goes, but all this time the M is trying to, so the excitation pulse is off, so the magnetization vector is trying to come to its equilibrium. The static magnetic field that is always there, it is trying to come there. So your Z direction, MZ of T, is a rising exponential. Of course, it is rising using a time constant T1, right? It is taking its own sweet time to come to that. Just to be clear, MZ of 0 plus is the value of the RF excitation pulse, meaning when you start, if what happens, M0 is very clear. You allow it to completely recover so that it is aligned into the static magnetic field, the maximum equilibrium value that it can get. But just for correctness, I don't have to allow it to, come back fully before I push it down. I can again push it down. The moment it starts to come up, I can again apply the RF excitation pulse, make it go down. Remember, my signal is only the transverse component. So the moment it's dephased, the signal goes down. So there is no fun for me to wait all the time. That means the signal is going down and down and down, right? You're going to hit the noise floor. So I don't want to really wait till it goes and then comes back and then measure within T2 time, right? The signal amplitude. I mean, if I want to repeat the experiment, I wouldn't do it. Rather, I shouldn't say like that. If I want only T2, then maybe I should be able to do it multiple times. So MZ plus is just a general representation of wherever you start at 0 plus. Okay, it need not be the final equilibrium value. That's the point. Okay, let's keep it simple. Okay, so now your longitudinal relaxation therefore can be modeled as also a rising exponential. In the rotating frame of reference axis, you see x dash, y dash, z dash, this vector m, right, mz is increasing. Okay, so why does this happen? This happens due to natural laws. Okay, so for all practical purpose, T2 is much smaller than T1. For tissues, typically these are the range. Tissue as in body tissues, right? T2 is in the order of tens of milliseconds to even some hundred, but T1 is hundreds of milliseconds. Okay, T2 star is much lower than T2. Okay, let's stop here.